know quite a few people just from being around astrophysics for some years, but I appreciate that people have come from all walks of physics and students as well as practicing faculty here, so I'm really grateful you're taking out an hour of your time. The way I'd like to do this is, feel free to interrupt me. There is a flow to the whole presentation I put together, but there are many ways where it can diverge, and I promise you I will not lose my stream of thought, so I'll be able to come back. So I encourage you to ask questions, no matter what kind of question you have in mind, and we'll do our best to have a quick conversation about it. So with that said, it really is a pleasure to be here. I have not been to College Station before, so this has been a treat for me. I've been in California for 11 years now, and the humidity is something I'm not used to. So it's been.
You're welcome.
Yeah, thank you, Casey. Considerate as always. I'll be talking about dark matter, and I'll give you enough of an introduction so that if you're already familiar with this sort of area of study, you'll be able to sort of refresh and see where I'm leading to in terms of how we measure things. And if you've not been exposed to it, then I hope it'll be interesting, and you'll be interested in pursuing a little bit of reading or work on your own as well. So let me start with a picture of the Jet Propulsion Lab. If you haven't been to California, go to Los Angeles. If you make it to Los Angeles, make it to Pasadena, and make it all the way up into the foothills where the Jet Propulsion Lab is. There are about 6,000 people that work there, and virtually everything that we, as a nation, as a human race, have sent into the solar system has been conceived of, designed, or built at the Jet Propulsion Lab. So it's a pretty exciting place to be. You can go to places like the Mars Yard, where they literally drive the rovers. Like they're carbon copies of the rovers that are on Mars, and whenever they've, on the planet, they've come across difficult situations, they reproduce them there and try and solve the problems and test engineering difficulties and challenges. And it's wild. And right now, big projects include a probe that it will go to Europa and send a lander there and drill. That should be popular in Texas, in order to go through the ice sheets and see if we might begin to detect life in the ocean below. So we also do astrophysics. We do quite a lot of astrophysics, from inflationary cosmology all the way to star formation and exoplanet science, galaxy formation evolution, and also heliospheric physics, study of the sun. So there's a lot that's going on. Come and look us up. There are tours all the time, and if you have a professional connection through myself or one of our colleagues, don't hesitate. It's a great place. So a lot of the science that I'm going to be talking about, I use this expression way too often, and I think I've only heard myself use it, so feel free to use it. Going down the rabbit hole. You know, when you think, oh, this is a fun problem, and you start working on it, and you realize that, oh crap, one more layer. Okay, one more layer, and I'll understand everything. And before you know it, you've drilled down, you've opened up 3 whole new areas of study nobody's ever thought of before, and it's really fun. You do have to keep sunlight on the problem, but a lot of what I'm going to talk about here is basically a whole bunch of rabbit holes that people have been dealing with for a while. So when I was first setting up the sort of progression of ideas, I still wasn't 100% sure how diverse the audience would be. So there might be a couple places that I'll just ask you to pay attention to me rather than what's written, and we'll just sort of methodically go along. In fact, this is the kind of thing that it's sort of a concise summary of what you could spend an entire semester or a year covering. Basically, here's the executive summary. There's a lot of evidence for dark matter. In fact, we've known about it for many, many decades, for the better part of 80 years, by studying the motions of galaxies and galaxy clusters and stars inside of galaxies. There's a lot of material out there that has a gravitational signature that cannot be accounted for by the census of all of the things that you can see. If you see things moving faster than the material that you can detect with your imagers, your eyes, your detectors, then that can, and for all of us it did, incontrovertibly lead to an inference that there's a lot more material out there than you can actually see. And then I hear overtones. That's cool. Maybe. Oh. All right. There's symmetry and everything. Is that all right? Thank you. Appreciate it. So what we've been able to do over the past 15 years, 20 years, is not only be aware that there is a lot of material out there that we can see gravitationally, but to get a very, very precise census of it. So I'm going to flip to a chart that'll be more meaningful for the folks here that have done a little bit of astronomy. So I'll put it this way. We have been able to map the echoes of the Big Bang, the light that's left over from when the universe first formed, and this particular moment in time when light was able to just stream freely, and because of how the universe has expanded, we can see it all around the sky at very, very long wavelengths in the microwaves, in fact. And it has the imprint of what the universe was like just a few 100,000 years after the Big Bang actually happened. And this is an actual measurement. This is from the Planck satellite. It's a measurement of what's the little brightening and dimmer parts of the sky. It's literally a map. So if you go to the night sky and you had that on your smart device or something, you could say, okay, there's where an overdensity is, there's where an underdensity is. And the statistics of that behavior, you can see it's not random. There's structure to it. There's some large structures and some a lot of high frequency structures, small scale structures. And that the amazing thing of that is that map, that alphabet soup up there, is completely interpretable with very simple physics, what turns out to be very simple physics. Never mind that it took us 50 years to figure it out, but once we did it, you'll notice I'll keep on saying we, because I really do feel that this is a community pursuit. This is all of us. So once we did this, we were able to map the fluctuation properties of this map to a model, which is this line on top of these measurements that reflect that fluctuation map. And from that, based on how the different knobs in this model get tweaked to produce this kind of a curvy line, we're able to extract amazing information about the global properties of the universe. One of which is how much dark matter there is. And it's the same idea as the original ideas with dark matter, that there's more material there than you can explain gravitationally. So here we see the gravitational imprint of that material. And based on that, we've determined that about a quarter of the total mass energy budget of the universe is in dark matter, and a minuscule fraction of that is what we blithely call baryonic dark matter. Basically, you and me and all the stuff you can see around, and the cats you have at home and the stars you see in the sky, all of that is regular matter, and the gas, the air that we breathe and everything. And that is completely distinct from dark matter. So that's an important thing to appreciate. So you can sort of sense now, it's pretty mysterious. It's very odd. Now, I'm aware that there are some particle theorists in the room, high energy physicists in the room, and so they will not be shocked to see a plot that spans about 40 orders of magnitude. All you need to take from this is that we, being clever, can take a problem like that, right? The simple problem that you think you can try and solve, and you can come up with ideas that fit your observations. And so what this plot on the left, which you don't need to dwell on, is representing the wealth of ideas that people have put forward to try and explain what dark matter might actually be. The thing is, we are made of quarks and electrons, and there are some basic forces like photons that communicate information between the particles that make us up. Why can't this invisible material be like that? And so you start coming up with ideas. It could be particle A, particle B, driven or inspired by different other areas of physics or pure creativity, for that matter. And so there are many, many ideas out there, and that's sort of encapsulated here. Now, this is this is a figure I really like. Everybody likes time, and sometimes you can make a sketch that makes you think about a problem in multiple ways in one single figure. And so it's this figure here on the left. So I'm going to apologize. I should have spelled out what the acronyms mean. Even though I am at basically at NASA, I do try and spell out acronyms at every opportunity. Even though in some circles you'll see acronyms made up of acronyms, there's a word for that. It's an acronym. Yeah. No, there's a dictionary term for that, but it's horrible. But anyway, so the DM stands for dark matter, not so mysterious right now, and the SM stands for standard model. It's basically the basic the theory that describes all of us and everything in that we can well, all the particles and forces that we've been able to observe. Now, here's what could happen. You can draw the arrow of time from left to right, and what is that showing you? It's showing you two dark matter particles that, by happenstance, might bump into each other, and they might produce two regular particles. This is an interaction that can happen, or that you can posit. Or you can go to the Large Hadron Collider or the collider of your choice, and you can basically go do that arrow towards the left, where you can take two protons, smack them together at very high energy, like I did the microphone, and hope and try to see what comes out, and maybe you would produce something that would be dark matter, and you would see it by the energy missing from your collision. And then finally, in sort of more broadly speaking, in astrophysics, and there are people in this room that do this. Seek them out. These are fun experiments. But you can put a detector deep under the Earth. It's made up of cleaning fluid or silicon or things like that, and you can put lights all around or detectors all around it, and then back away slowly and wait until you see something glow. The short version, and that would be from a posited idea that could happen of a dark matter particle going through everything because it doesn't interact with most things, and just by good chance interacting with somebody in your experiment and detecting it. So all of these are ideas for how you might try and learn more about dark matter. We know it's there. We know how much there is in the whole universe, but we'd really, really like to know what is that material, like for real. Let me put this in perspective. There's dark matter, because we know where we are in our own galaxy. There's dark matter going through each of us right now at 200 kilometers a second, and there's about the mass of about a third of a proton in every cubic centimeter, and I have no idea how to translate into inches, so I apologize. But you get a sense, right? So that's a lot of material, and it's going through us very quickly right now. And does it impact the world immediately around us? Well, not in a direct sense, but it's definitely impacted the global evolution of the galaxy, our very home, and certainly the greater environment in the universe we live in. So what I'm mainly going to be speaking to you about today is an alternative probe into trying to understand dark matter. So I showed Alice and the rabbit earlier, so this will be many layers in the onion. So if you would like me to pause or step back or do something that's a little bit different, again, I encourage you. I really wholeheartedly mean it. Feel free to interrupt me. So there are other ways to look for dark matter. Now, this is perhaps I'll skip over this in large part, and I'll just use words. The idea is that all right, so we know that there's a lot of dark matter out there, and we know how much there is in the environments around galaxies like our own. The detailed properties of dark matter could end up giving you a different distribution of dark matter concentrations across a Milky Way type galaxy, across a galaxy in general. And the idea is that if you could determine the properties of that structure of dark matter inside of a galaxy, you can take that information and back it out and learn about the physical properties of the individual particles that make up dark matter. I'm realizing this is probably a little bit too much, so maybe what I'll do is I'm going to do a little skip here. I'm going to start with a picture, and then I'll back this up a little bit. So this is fun. I'm rather fond of this picture. It's been around the block a few times. If you've gone to colloquia where people have talked about small galaxies in our own galaxy or about cosmology or dark matter, you've seen some variation of this. But the basic idea is for you to look at what is the difference between these two panels. See, they look similar in a sort of a gross way, right? They're sort of elliptical and stretched in a similar way. And that's because these are simulated galaxies. So these are galaxies in a box. Right? Put some conditions into your code, and you let it evolve as the universe expands and gravity works. So I'll point out what may have jumped out at you right away. That on the left-hand side, you see a lot of structure, a lot of small-scale, bright distributions. And on the right, you don't. You see some, but not so many, and not so many of the very, very small ones. So this is sort of the this is the hook. This is the hook about what we're after. On the left-hand side, this is the kind of environment that you might expect in a galaxy, like our home, the Milky Way, if dark matter has a certain set of properties. If it really doesn't interact with itself, if it really doesn't interact with regular matter, if it's very cold, it has a very sort of a slow natural velocity, then you end up with this predisposition to clumping things a lot more than you might otherwise. And in fact, on the right-hand side, it's what we would call a warm dark matter scenario, which is consistent with a whole slew of particle models that people have explored, and you end up with a lot less of the small-scale structure. Yes? The question is, what is the color coding? This is just showing you it's related to the density of the dark matter. So it's this. So exactly. So the very center is by far the most dense, and that's because you have a concentration from all of the smoothly distributed dark matter that's at the bottom of the potential well. So it doesn't have a finite surface. It sort of extends. It gets thinner and thinner as you go away from the center. But the highest concentration is by far in the very, very center. And actually, I'll give you a little bit of a teaser of something that's sort of interesting and problematic that's dependent on that. The center is really, really, really hard to calculate correctly because there's so much that's going on. It's a really volatile place. You might think that, space is, well, space is empty. But once you get towards the center of a large object like the Milky Way or like other galaxies, it gets, things change really rapidly. Within tens of millions of years, you could get very rapid evolution. And you'll appreciate when things are billions of years old, well, that's a large factor. Yes? So the question is cold dark matter, and can it emit light of any kind, I think. So it doesn't, does it interact enough to equilibrate? And it does reach some state of equilibrium so that you can, the beautiful thing about creating a simulation like this is that then you can go into your simulation and you can ask the question, what does it look like? And you will find that they have some kind of an equilibrium state, as long as they don't interact with something else that they're zipping by. Because then other interactions, gravitational interactions, can distort and change and heat or like expand or make to contract. So that's a fun question, and that's also related to what's going on in the center. You get a lot of dynamical evolution of the structure, but nothing's really fully steady state. There's a constant evolution of these structures, which makes the problem hard, but we're brave. We can do this. So, the idea then is that if you were simulating, well, I apologize here. So the idea is that on the one hand, you would like to explore what the evolution inside of galaxies looks like for different kinds of dark matter scenarios. So this is a cold dark matter and a warm dark matter scenario. One that, the way it's presented here, the way it's presented here isn't quite as visually stunning. The contrast of the light isn't that good. It's okay. It's okay. It's in spirit. What I wanted to point out is that we had the cold dark matter and the warm dark matter, and then there's another broad flavor of dark matter that's called interacting or self-interacting dark matter. All you need to take home here is that we are beginning to create simulations of galaxies and larger systems that use different assumptions for the properties of dark matter beyond gravity. This is more for the people that are in this field. This is sort of a table of several published types of general dark matter scenarios along the lines of the pictures that I showed you that some of my collaborators and I, which I realize now I horribly forgot to acknowledge, so I need to come back at the end to do that, that my collaborators and I are taking to try and answer these questions of dynamical evolution. Like, what does the structure that you predict look like when you are considering different dark matter properties? Does that make sense? So you're trying to do like the prediction, like because you have the comfort of a warm room and a cup of coffee and a computer in front of you, you can go and simulate these different universes and make some predictions for particle A, B, C, D, Z. This is the kind of behavior that you expect, it's a pretty important problem because in effect the kind of thing that we see in our Milky Way right now is actually a pretty small number of things. Let me drive this point home with this figure again, because it's a fun figure. Right? There are a lot of very small scale things on the left, and hardly any small scale things on the right. You agree? One person say something. Okay, rock and roll. Thank you, thank you, thank you. So one way to represent that is to just go and count how many things do you see at high masses, medium masses, low masses, and that's what this is showing you. This is just showing you how many in each mass bin. So the most massive Milky Way satellites, dwarf galaxies, satellite galaxies, are this many numbers, and then there's another number, these many at these different mass ranges, and there's been a pretty major breakthrough about a year ago from the Dark Energy Survey. Some people here are involved in that has discovered more, and this is not an updated plot. But the point that I'm going to make here remains. If you go back to that figure on the left that showed the huge number of structures, of small-scale structures, this is what you predict. That's what you predict. And that's a lot of space between these two. So one is, how many of these smaller scale galaxies have we been able to observe today? And how many would you expect if you said, okay, here's my universe in a box, and this is my prediction? So this is, herein lives 2 decades of intense controversy and discussion, and I've seen some yelling at conferences. It's very passionate. No food fights yet, but or that I've seen, I don't know. But basically, you look at this, and half of you might say, "Oh, that just means that model's wrong." Some people are very passionate advocates for that model for very good reasons, because it fits so many observations so well. But then the other half of this room might go, "Oh, well, that's Milky Way satellites. To see them, they have stars. So maybe the rest are there, they just don't have stars. And we just need to understand the astrophysics." And that's why you need to go back to your universes in a box and really, really understand the complexities of the problem and figure out how to bridge this gap. Because the truth could be one or the other or something in between, and there's a lot to understand. So, So for those of us that work in this area, you know, let's go for a cup of coffee later. And for those of you that don't, you get a sense of how interesting the problem can be. So now what I want to do is I want to sort of set the stage for how we try and reach a prediction for how these different scenarios might manifest in astrophysics. Question? So the question is, what does hot dark matter prediction on the spot look like? So, so everybody appreciates, at least at a qualitative level, that I've already spoken about cold dark matter and warm dark matter, and that has to do with basically the characteristic velocity speed of the individual dark matter particles, so that by the time you look at very large scales, you can wipe out structures that are those small scale structures. The problem with, as you turn that knob, you would predict that all of these wouldn't exist. So hot dark matter has been ruled out for a long time just by having observed how much structure there actually is that we do see. And this sort of space that I'm talking about, interacting dark matter or warm dark matter, is what's allowed by observations. There are quite a few constraints that are out there. There are lots of models that have been ruled out. It's just that the parameter space, the discovery space, and what is still allowed is still pretty fundamental. Is that fair? Thank you for the question. So wouldn't it be nice if you could distinguish between these scenarios without having to count on there being stars or gas? If you could just, I mean, after all, we're talking about these lumps and clumps of material. Wouldn't it be great if those lumps and clumps of material you could be sensitive to somehow? Well, so let's go back. Sometimes it's nice to you know, step back and go to your basic principles. And so let's do that, and let's ask, in what capacity was dark matter first discovered? Well, through its gravity. So is there any way that the gravitational signature from all these structures, all this material, could give you something that you could detect? Now, within the Milky Way, there might be some ways. There might be a way by looking at the streams of stars in the Milky Way. There might be a way by looking at the kinematic properties of dwarf galaxies. There's some ideas that are being explored that I think are pretty exciting, quite exciting. The method that I'm going to discuss involves a phenomenon called strong gravitational lensing. And some of you have heard of it, maybe even have worked on it, but the rest of you are familiar with it too, actually. It's just that you haven't seen it in terms of its gravity. But if you've ever been to a pool, and you know how if the pool's been splashing, you can see some bright slivery light on the pool bottom. That's actually caused by the ripples on the surface of the pool that's focusing the sunlight extremely intensely in certain spots. And of course, it's moving in real time. Whereas if you're on astronomical scales, it doesn't move very quickly. But that's just gravitation. That's lensing, and the gravitational lensing is the same kind of effect, but from a gravitational focusing rather than the water or a lens focusing. You can also, oh, actually, I have a nice graphic for that. So let me show you what gravitational lensing looks like. The idea is that, well, the universe is a big place, and there could be an object over there that just happens to be there, right? And then just by chance, there could be an object over here that just happens to be there. If you have enough random directions to look, once in a while, 1 in 10,000 times, you'll get something that's lined up like that. If this is massive enough, I will end up seeing multiple images of that object because the light is going through the gravity and it's being focused, and you can end up with multiple images. And that's what's represented here. There's a faraway object here on the left. Right there. Oh, love it. One of the things we're looking at now is using lasers to communicate with satellites, which is pretty cool. Optical communications. Then there's the massive galaxy, the water bottle. And then here's where we are, and what you can end up seeing is 1, 2, 3, 4 images of the single object. You can practice this with any kind of a glass that has sort of a stem and a base. So wine glass works well. that's a candle. If you hold your glass just so, you see 1, 2, 3, 4 images. If you hold it just so again, you see 2 images and a fainter central one. And if you hold it down the stem, you see a full, what in gravitational terms we would call an Einstein ring. It's exactly the same effect, except we get to see this on cosmological scales. So here's a little montage of real images of strong gravitational lenses. These are all taken by the Hubble Space Telescope. The column on the left just has the grayscale reversed, so the black is bright in this case. And the first 3 columns are all gravitational lensed quasars. I told you the rabbit hole goes deep. We have to learn more and more physics and astrophysics as we go along. But the column on the right is galaxy lenses. So the background object over there is a galaxy, for this column, and the background object over there is a quasar for these objects. And we'll get into what a quasar is. But I want to make the connection with the first few minutes of our discussion here, which was how much structure there is, and can you possibly get a sense of how much you can detect. So there's the graphic, the sort of ray trace cartoon of lensing for light that goes from the left to the right and can form multiple images. And here is, this is the Via Lactea simulation, redshift 0.6, where I've just overlaid geometrically how big a gravitational lens would look like on that profile. So the images form near the projected center compared to where the virial radius, the maximum extent of a given galaxy. So you can see that there are advantages and disadvantages here. In a sense, what we're trying to do is, if you look at this column on the right, I have just 3 convenient representations of this dark matter structure, substructure. This is a scenario where I guess this circle is about that big. This scenario, that's sort of like the cold dark matter scenario where we have a lot of structure. And this bottom one would be sort of an extreme warm dark matter scenario where there aren't that many structures. And in a sense, we are asking the question that I posed about 10 years ago, which is, if you can make certain measurements of your object here, can you say something, can you distinguish between case A, B, and C? Can you measure that? So the answer is going to be yes. Yes? So if I could rephrase the question, tell me if it's correct. When you see something like that in your image on the sky, how are you sure it's a gravitational lens and not just 4 objects that happen to be close to each other? Yeah, no, it's a fantastic question. And it took, so the first lens, gravitational lens, was discovered in '79, and it took a little while of discussion before we sort of converged on a way of really evaluating these things. One way is by getting spectroscopy of all of the images. Because if you can get the chemical imprint of an image, it really is like a fingerprint. And if you get an identical fingerprint and you see this very characteristic geometry, and you can write down a very simple model, straightforward model that explains it to a large degree, then you would be able to convince peers that don't like you. Great question. In fact, so one of the things that I've set up, it's called the Master Lens Database. If you Google it, you'll find it. Everybody's welcome to use it. You need a password to get in, but just drop me an email. You can just go through Casey. And it's a massive compendium of all known strong gravitational lenses. And one of the things that we keep track there are objects that look suspiciously like lenses that aren't, because we could use those to learn when we have the Euclid Space Telescope or the W1 Space Telescope, future observatories. It'd be really nice to know how to automatically detect such things with confidence. Okay, and so now This may have been a mistake, but I have equations, and it's very important because it's important because the main point of this equation is actually it's very straightforward, as I'll point out, but it's extremely powerful, extremely powerful. So you appreciate if you have a candle there, a galaxy there, and you have your lens along the line of sight, and you form these multiple images, what's going to happen? The travel time of light that goes to the first image and the second image and so on is going to be a little bit different. And this equation encapsulates that. It tells you, and this is all that it tells you, the amount of time that it takes light to get from way over there to your eyeball. It depends on, depends on geometry, so distances, depends on distances. It depends on the alignment. Are you bullseye or a little off to the left or whatever, right? So that's simple so far. Relative distances, the geometric alignment, and then this is the most important part. It depends on how much material is there, what the gravitational potential is. If your projected potential is this, then the light travel time of light will be this. And so if you can somehow measure that light travel time, you can back that out and you can learn about the projected potential. And I think you're now suspecting or have already come to the conclusion or to the connection that I was alluding to earlier. If you have a way of connecting the projected potential through some kind of an observation, then if you have lots of little bumps and wiggles and variations in that potential, then you might be able to get that from an observable as well. And this now you'll see why I stacked the deck a little bit in the types of objects that I was presenting. The characteristic 4-image lensed quasars. There are many kinds of lenses, visually speaking, and I'm happy to talk about them, but my goal here is to talk about the primary, a high sensitivity tracer of dark matter substructure, and so I'm talking about these objects. Because a quasar, it happens to be an extremely massive black hole, about 1 billion times the mass of the sun, that is bright because of material falling on it. And so through the accretion, through the friction, that produces light, and you end up getting quite a lot of luminosity, quite a lot of light outputting. Well, the other thing that happens is because it's very compact, even a very massive black hole is smaller than our solar system. It's tiny. As material gets accreted, well, it's going to have weather, not to put it too finely. It's going to have fluctuations because it's a very compact, astronomically speaking, structure. And so on short time scales, on times of days or weeks or months, the brightness is changing all the time. It's getting brighter and fainter, brighter and fainter. And what does that tell you? If you could create a movie of a quasar lens, you will see one image brighten and then dim, and then another image will brighten and then dim, and so on. There's a sort of syncopation in the signal that you would be able to detect. And that will tell you what the difference in light travel time is. If you're observing image A and B, and you can see these brightenings and dimmings, you sort of take these fluctuations and correlate them with each other, and you get the difference in light travel time. Isn't that insane? It takes billions of years for the light to get from over there to our eyeballs, or to our Hubble Space Telescopes, or the Hubble Everly, or whatever you're using to observe this. But yet, I'm stating this, we can measure that difference in arrival time to better than a precision of a day. So 1 day over several billion years is sort of the scale of the sensitivity that we have today. I'll give you one more teaser. I've given you 2 or 3 teasers earlier for things that we've talked about. To solve the problem that we are seeking to solve here, we're going to have to measure the precision, that time delay, that difference in arrival time, to precision of about ½ an hour. So we can't quite do that yet, but we know how we can. So there we are. Oh yes, this in fact, I love this map. this is showing 4 images graphically, right, from a model, but fit to data. So there's 1, 2, 3, 4 images. And again, the contrast isn't quite doing it justice. But what you're seeing here, it's a contour map. And it's showing you the arrival time of light. And you get the images forming at the maximum, the minima in the time delay surface, and at the inflection points. And if you've done optics here, that's exactly Fermat's principle. You get images forming in any kind of a lens where the light rays pile up. And that's where you get the first and second derivatives, the special cases in a surface like that. Sort of cool, right? And so there's an overlay of the actual image. And so this the time delays are directly proportional to the projected potential, and so the fluctuations of the projected potential from dark matter substructure will give you something that's a little bit different from what you'd expect otherwise. And the thing is that the image positions depend on the derivative of this equation, and how bright the images are depend on the second derivative of that equation. So what is that really telling you? The main thing that I would like you to get out of this slide is actually this. Actually, here, magnifications are telling you about what's going on really where the images form, so where the actual images form, because it depends on the second derivative of the projected potential, and anything that's a second derivative is like extremely sensitive to small changes. The exact positions of where those images form are less sensitive to the small fluctuations, and so you can, if you have fluctuations of the potential, you could tweak things a little bit, but then the differences in arrival time, they have a much greater sensitivity of area around the images. Now that's useful because if we go back to this little graphic, remember, we're only looking down the barrel of the gun here. We're just, we're looking at a tiny little bit of the whole galaxy, the whole galaxy with its dark matter. And so if through some measurement you can end up having a sensitivity that is much larger than just right exactly where the images form, that can tell you about global properties with the study of just one object or a small number of objects. So that's pretty cool. So, it's a laser pointer. That is freaky. What is in here? Oh my goodness. Okay. All right. So I'm observing the time, and I want to be respectful. So I am going to. Here's why I'm hesitating, because there has been so much incredible work in this field, trying to use observations, different kinds of observations of gravitational lenses to try and back out the dark matter substructure question. And I had a variety of sort of acknowledgments of several methods and people that have done this work, and I'm just afraid I'm not going to be able to go through all of that. Here. This at least has some of the key names, so I'll at least do this. So succinctly, there are ways of using different types of gravitational lenses to identify single subhalos, single little dwarf galaxies, which is really cool. Like, imagine this. Gravitationally, we have published, we have demonstrated that there are individual beasties that you can detect through this weird gravitational signature from gravitational lensing. And but remember, what we want to do is not only go and collect butterflies, and I don't mean that facetiously, but it's not sufficient to just know that, okay, there's one person, I'll name it Jennifer, but we'd like to understand what it means for the whole population, like globally what's going on, because ultimately we want to compare those models and back out to the particle physics. That's our ultimate goal here. And so there have been individual detections, and very, very brave and mathematically adept individuals in the community have done some spectacular work actually taking detections and non-detections and mathematically extrapolating to what the implications are for the population. So, Dalal and Kochanek did an exercise like this about 15 years ago. Simona Veghetti has done spectacular work in this, and I would say that she's been just a pioneer in this field. And Yashar Hezave has taken a different approach using ALMA observations. So many of you work on ALMA data, where you get to see sort of in frequency space, you get to see the structure of a strong gravitational lens star-forming object, and it can give you information on the substructure there. And it's very creative work that has also been explored through simulations, through n-body simulations, and that's the work of Lee from the University of Durham that I think is sort of it's painting like a picture as it stands right now, and we are it's a growing field. So what I'm particularly excited about is how do we go to characterize full populations of the substructure of these populations. And the first thing we need to do is to sort of understand what would happen if you had, okay, let me back up a little bit. So now, let's enter the world of gravitational lens modeling a little bit. Lensing is, in its simplest form, extremely simple. You could take the equation that I had up earlier, and you can do a lot with that. When you start adding perturbations and more complexity from nature and so on, it can get very complicated. It's information rich. Shouldn't call it complicated, really. But it is challenging. You have to think deeply about how you do these different nuances. Okay, so if you create a model of gravitational lens, so you find one that you think looks beautiful, you put it on your phone. Like on my phone, I have RxJ 1131. I'll show it to you later. You can create a simple model of it, and that's great because you know what ingredients you put in to create that model. So you can control the universe in one limited sense. Not just when you have lunch, but you can control gravitational lensing too. And then one question that we wanted to ask was, if you artificially put one small structure right there or there or there, could you see a signal from that structure? This has to do with that region of influence that I talked about. So this has to do with this that I asked you to pay attention to. Time delays will give you sort of a long-range zone of influence. Now, it turns out that that is true in many cases, but not in all of them. And so we've done this experiment where around different lenses, and I'll show you 3 or 4 right now. Here's the image, PG 1115, 1, 2, 3, 4 images, and the lensing galaxies there in the middle. And in these images here, this is a little clearer, 1, 2, 3, 4. Except this is, you can see there are different color codings in these sets of figures. What the colors are showing you is the areas where if you put a small structure, a small subhalo, you will get a measurable effect. And each panel is for a different mass halo. So this happens to be 10 to the 10 solar masses, so it's a pretty large satellite galaxy. And it gets progressively smaller and smaller until we get down to small values. To not vary the lead, you'll see larger effects in a minute. But for 1115, you see that there's a region of influence there for sort of a high mass halo that doesn't look huge. Okay, let's go to B1422. It's another pretty image, a pretty lens. 1, 2, 3, 4, and here the lensing galaxy isn't quite visible in the particular wavelength I show here. And for a 10 to the 10 dwarf galaxy, you can see it's quite a large region of influence. Not much influence on the observations down here, but in this one, quite a lot. And as you go down to smaller mass subhalos that you've placed there, the influence gets smaller. Now, this is the one that I have on my phone, RxJ 1131, and you can see it's a very large range of influence. Now, this is significant because it's going out. Remember, this is for just placing one single halo there at each position and seeing what the effect is. And you can see that the effect continues down to 10 to the 8 solar masses, which is going down to smallish dwarf galaxy scales. And then finally, the one that I've chosen to show here, another one of my favorites, HEO 435. And you can see the 1, 2, 3, 4 images and the lensing galaxy in the middle. And the region of influence is quite considerable. Now, the reason we did this is because we wanted to get a sense of what kinds of objects, what kinds of lenses have the predisposition to containing this extra information. So this was sort of a stepping stool in the full problem that we wanted to do. We've done more work in that area. But fundamentally what we want to do is what we're presently calling gravitational topography, which is using the time information to get a broad vantage point on that time delay surface out to large distances. And it looks a little bit there was one slide that I'd slotted in there that is missing. So I apologize for that. So I'll do this. So the idea is we need to work out a methodology for going between the observations that you can make and the information you can get from the cumulative effect of that structure. And so what we've done is we've created, we've modeled, we've created a methodology that lets us calculate all of the different ways that substructure can affect your observations. So this is why I use the example of if you put one subhalo there, can you get an important effect or not? If you put a subhalo over there, can you get an important effect or not? If you put a lower mass halo over there, can you get effect or not? Then when you take that to the next level and you put down full populations of substructure, like we talked about for the first part of the talk, then you create one simulation and you see what the observable effect is, and then another one and another one. You do this thousands of times. What can you do to take those those distributions of effects that you get by having done those realizations and invert it basically, so that when you go and you make your observations, you can say my substructure looks like this. It has so much material. It does or does not have material below a certain level. This is a problem that we've been working on for a very long time, and we cracked it. And what I'm going to show you is preliminary, and it's not a pretty picture, but it's a very meaningful one. There's a way of doing calculations that that let you explore your parameter space in a very effective way if you've written down the right equation, the right things that you want to explore, which we believe we've managed to. And the idea here, if you just look at the plot on the left, is for this particular scenario, the vertical line is showing you truth, because remember, we can control truth in our simulations. So there's the blue line there, there's the blue line there, and this is showing you that for a particular example and for a particular set of measurements, that it's possible to recover how the total amount of structure that there is in small-scale beasts to some level of confidence that is described by the shape of that curve. And in this case, what we were testing was a truncation That's just under the dwarf galaxy mass scale, 10 to the 7 solar masses. And remembering that this is using a single object, we're beginning to see that one can extract the information that one wants. So this is sort of the state of affairs right now. So the problem of dark matter is a pretty fundamental one. We're pursuing it many, many, many different ways, from direct detection, large hadron collider production, many astronomical probes, and for many of us in the community, it's been very compelling to try and measure how much substructure, what dark matter behaves like within galaxies that are cosmologically distant from us, because we get a very special vantage point that way. And if you can do this kind of a measurement over many objects, well, then you can start figuring out how dark matter behaves in different mass galaxies and at different cosmic eras. So it's very tantalizing, very exciting. Sorry, an app popped up on my screen, but not there. That's good. And we believe we've arrived at a methodology that lets us do that, as long as you can get the right kinds of observations. This is a main reason why we wanted to explore this, to work out, first of all, what is possible, and then to work out how do you get there. And for the examples that I showed you from our universes or galaxies in a box, the kinds of measurements that are required aren't quite achievable yet. We need, first of all, to improve our position measurements a little bit more. That's something we can do now with more Hubble Space Telescope observations, with the James Webb Space Telescope, which launches late next year, and through future ground-based observatories. We need to measure time delays, the difference in arrival time, really precisely. And that's not possible quite yet, but we're exploring space telescope ideas and other measurements that might be possible, either with Hubble or from the ground, since even getting measurements for one single object would be very, very good. And sort of riffing on that point, we could sure use more objects, like a lot more objects. So all of you working on the dark energy survey or the kids survey or whatnot, please keep looking. All right, I'll help in any way. In fact, in October, so next month, happy month, there's going to be a Gaia exercise at New York University, where the project I've submitted is to see if we can detect more four-lens quasars in the Gaia dataset. If anybody wants to play, open to ideas. But that could help a great deal, having more objects to play with. So in summary, I think I've covered the main summary points. So I'll leave up the pretty picture, and just want to finish by saying that now this is, I prefer to be able to give you some earth-shattering results, but this really is sort of a step in the progression. And as a field and as a community, we've been advancing enormously the past very few years. And one of the really gratifying things has been that our mathematical and analysis sophistication has grown with leaps and bounds because of people like Simona Vegetti and Yashar Hazava and others, and I think in my team as well. I think the future looks very, very promising, and we will be learning a great deal about the properties of dark matter in the next few years. So stay tuned, and I appreciate your attention and your questions. Thank you.
Are there a couple questions? You didn't mention about the fact that the light curves don't exactly match each other for the lenses. There is difference between one lens and another lens in the multiple lens image. Does that contain information of predictions from the models that we cut off of dwarf galaxies of mass of 10 to the 7? Can you use those differences in light curve variations?
So the question was, if you're able, when you're able to make that movie for one object and see the flux variations in multiple images that you try and match, that sometimes you can see that there are differences, that they aren't 100% identical. So you can sometimes get some large differences that are caused by microlensing, which is by this sort of compound lensing effect by, literally, individual stars in the lensing galaxy. And as the stars zip around, they can cause order unity, so very large fluctuations that are unique to each image individually. So part of the question was acknowledging that that can happen. Is there information in there? So there's two parts to the answer. So one part is that it doesn't always happen. If you can get the information you need on a relatively small time scale, because some of these time delays are just time delays of 6 hours or something, like very short. And if you can get enough information in a modest period of time, so out of a few weeks of observations or a couple months of observations, you could be in a situation where you do not get much of a microlensing signal, because those timescales are between weeks and years. And so, but you can probabilistically account for that in your matching model. The second part of your question is there information in there? And it's a very, very definite yes. In fact, you get different statistical properties of microlens variation, like more or less, or it's flatter or less probable to happen, depending on the relative fraction of smooth to compact material at each image position. And this is a really fantastic paper by Paul Schechter and Joachim Wamgans. So if you're fortunate enough to have a long-term signal, a light curve measurement, and you do your matching of your light curves, and then you look at the deviations in image 1, 2, 3, 4, or minimum 1, minimum 2, settle 1, settle 2, the statistical properties can tell you about the fraction of stars to smooth dark matter, which is another bit of information, and the structure of the quasar itself. And there's a series of papers by Blackburn, by Chelsea MacLeod, spectacular papers that explore this. And I highly recommend them because they're also very mathematically sophisticated. Fun question, I appreciate it. I intentionally didn't get into microlensing, so I appreciated having the opportunity. Mm-hmm. Yeah. So the question is, how many dark matter particles are there, or could be? I think that's a very insightful question, because we often talk about what is low dark matter particle, drum roll, and one person might say, oh, it's this supersymmetric particle, the lowest supersymmetric mass particle, or something. But the truth is, why should we have all the fun, right? Well, the dark matter could be an entire dark sector. There could be dark hydrogen atoms having dark photon parties, right? Absolutely. And the cool thing about the idea of having a whole family of a dark sector, that's actually what it's called, is that also can give you predictions. Because if, like in a hydrogen atom, you can absorb light and emit light, well, if you had something equivalent in the dark sector, then, well, that's still an energy sink and an energy source. And that can actually influence things that you can observe. For answering questions like that, you can go, for example, to the cosmic microwave background, the imprint of the Big Bang that I started out with, and you can see if there's evidence for an energy infusion signature at the very, very high frequencies. And there's a really wonderful literature in that area. Tracy Slatcher, she did a spectacular job doing some calculations there. Francis Yancey-Racine has done some work there, and there's some very strong constraints. So what am I trying to say? It's entirely plausible. Some basic ideas have been ruled out, but again, why should they have all the fun? There's a question over here.
The source, here you're using quasars.
Yes.
So these are presumably the accretion disk around the black holes.
Mm-hmm.
So then how does the substructure, if there is
Mm-hmm.
of the accretion disk play into this? Because you are mapping, so you're basically zooming in at certain points on the accretion disk. And if there are substructures with different image, you may be viewing at slightly different points.
Mm-hmm.
And if there are fluctuations, then you need.
Sure. So the question is, since the category of objects that I am concentrating on are quasars, these black holes with accretion disks, and there could be different concentrations, different fluctuations in the accretion disk itself. I would call that weather. Right? You could get little tornadoes and storms and things. I mean, absolutely. You can get fluctuations that are brighter in this spot or that spot. And how does that impact the kinds of observations that I'm talking about, where that is the source, and I'm looking for these other fluctuations? So I think the most crisp way to answer the question is that as long as the quasar is fluctuating, it's likely that you'll see that fluctuation, whether it comes from hemisphere A or B. You'll see that fluctuation in both in all image pairs, and as long as you can map those fluctuations, that's okay. Like the fluctuation that we're trying to measure is actually more of an anomaly from a simple scenario, and it doesn't matter for the time delays. It doesn't matter so much what structures the light does or doesn't go through. What matters is what's happening from a much larger projected volume around each one of the images. Yeah. Mm-hmm. So the question is, in sort of thinking about actually designing experiments, if you need to sit down and figure out how to make the measurements, what kinds of detectors or things you would need to have. So there is a lot that you can do with X-ray measurements, which you alluded to, but what we have, what I have here is all optical images, and the reason is quasars vary. The bluer the wavelength, the more they vary. And it's just the nature of the energetics. Once you've gone down that potential well towards the inner part of the accretion disk near the black hole, the energies are coming out. Well, they are coming out in X-rays as well, but in the blue, optical, and ultraviolet. But then these quasars are redshifted. They're at cosmological distances that have shifted the light to basically optical wavelengths. And so the greatest fluctuations that span sort of a large sort of volume here are comfortably covered by optical, which in a sense is an easier area to work in. Except I would have to take over Hubble for a long time to do this, which I'm going to try to do. Yeah. Or you build a new observatory platform, and we've been working on an Explorer scale project called Omega, whose goal would be to accomplish this measurement. But in terms of the detector, the technology, the basic approach, it's an optical detector, and there are definitely challenges and subtleties to how you make the measurement, photometric precision, the robustness, the period of observations that you need to support. So it's definitely a fun challenge. But in terms of detectors, optical works very well. Appreciate the question.
Thank you.